Hi students, now we are meeting after a long time. Now we are starting the new chapter, that is Unit 2, Chapter 3, Current and Electricity. Friends, as your second PUC examination is concerned and your competitive examination, any kind, it may be CET, NEET, IIT, AIEEE, AIMS, architecture, etc. Any kind of examination is concerned, this chapter plays very important role. And among 14 chapter, the chapter Current Electricity is the biggest chapter, which covers 15 hours of teaching hours and carries maximum marks out of 14 chapters. That means 13 marks in this chapter total. Out of 13 marks, so 1 marks, 2 marks, 3 marks, 5 marks, all type of questions will be asked from this chapter. Now, so before going in detail this chapter Current Electricity, let us revise what we have studied in the previous 2 chapters, that is in 1 and 2, electric charges and fields, electric potential and capacitance. Friends, in the last 2 chapters are covered under one topic called as electrostatics. Then what is meant by electrostatics? As we know that electric charges are generated due to friction, due to induction, or due to maybe the conduction. These charges are at rest on the surface of a charged body and they'll produce some effects that only we studied in the previous 2 chapters and their applications. Today, if these static charges possess motion or if their charges are moving from one place to another place, what happens? From our basic knowledge, we know that the flow of charges constitute electric current. That means flow of charges producing the electric current. That's fine. But the question is, why the charges are flowing from one place to another place? To flow from one place to another place, what kind of medium or connecting bridge is required to transport the charges from one place to another place? So if the charges are flowing one place to another place, if they flow very easily or if there is any opposition, and if the current or the charges are flowing from one place to another place, at what rate they are flowing. So all these concepts will be studied in this topic. So let us start with the introduction. So now friends, let me take 2 simple metal spheres. Okay, I will take 2 metal spheres. So once I take 2 metal spheres and they are charged for different potentials, say it is V1. I will take another one metal sphere, say this is V2. It is charged to V2. Now V1 is charged with some potential, say V1, and V2 is charged with another potential, say V2. If these 2 charges metal spheres are charged, then condition applied, there must be a potential difference. That means what? V1 should not be equal to V2. Condition applied. V1 should not be equal to V2. So if V1 and V2 both are not equal and if they are kept apart in the space, the charges from one metal sphere to another metal sphere will not flow because there is an insulator here. This insulator is now nothing but here air. Air is there. So already in the previous chapter I talked about this, polar dielectrics and non-polar dielectrics. In that, air is also acting as a dielectric. Air is dielectric and it acts as the insulator. So that means what? There is no flow of charges from one metal sphere to another metal sphere or vice versa. Then, if I join these 2 metal spheres by a bridge, by connecting them. So let me take a wire or a conductor, join them. So once if I join suddenly, so now this is what? Conductor. In our common language you can say wire. So then if there is a potential difference between 2 metal spheres, and if they are connected by a conductor, which is a conducting metal or conducting wire, then there is a flow of charges from one place to another place. Let me take this one. So let me take V2 is high, V1 is very less. So it's greater than like this. V1 is here, V2 is here. If the potential of the metal sphere 2 is higher than the metal potential sphere of the sphere 1, then there is a flow of charges from one place to another place. That means what? If two potentials are considered, if two potential ends are considered, first and foremost, what we need? We need potential difference. What we need? We need potential difference across the ends. Very, very important. Across the ends of what? Ends of conductor. Time being, I'll take this wire only, the conductor. So we must need a potential difference. Then what exactly the meaning of this potential difference? Very simple logic. Suppose let us see here. Pay attention, very, very important. So now here is we have a tap. Here we have a tap. Let's say corporation tap. Let's say. So water is coming, and you are residing in the third floor. So whatever the speed, the pressure of this tap water is there, that pressure is not sufficient to lift the water to this floor. Then what will you do? There is a high pressure. Here is low pressure. Two pressure zones are there. Suppose if we allow the water to flow from third floor to ground floor, it automatically flow because high pressure to low pressure. But if you want to set this low pressure water or tap water to the third floor, you have to set the pressure difference. At that time, so once if you set up the electrical motor here, so what electrical motor will do? This electrical motor will uplift the water to this third floor. So what we set here? So now by using this motor, we set a high pressure here. We set what? High pressure here. Now it becomes low pressure. It is low pressure only, high pressure only, but by applying this artificial pressure, so this becomes low pressure. At that time, automatically water will lift from the ground floor to third floor. Then there is a pressure difference is required. This pressure difference to uplift the water from the ground floor to the any floor. What we required? We required pressure difference. Similarly, to flow to allow the electric charges to flow from one potential to the another potential, one conductor to the another conductor, one end of the conductor to the another end of the conductor. What is required? Potential difference must be required. I suppose it is clear to you people, right? So now, friends, this potential difference itself plays a very, very important role in the conduction of electricity. So now, let us proceed to the next concept. Suppose if these two metal spheres are equal, suppose if I say V1 is equal to V2, if they are connected by a conductor, then what is happening there? There is a flow of charges, but not like this. So we can refer it as a steady current. Constant current exchange of the charges will take place between the metal sphere, and that flow of charges itself is referred as a steady flow of electric charges through the conductor. That is called as steady current. I hope it is very clear to you people. With this small introduction, let us proceed to the heading called as electric current. Then, what is electric current? So now, as I said here, the flow of electric charges through the conductor from one end to another end is called as electric current. But if I write the proper definition of electric current, the time rate flow of electric charges, the time rate flow of electric charges through the conductor. So if I write this, I will get the flow time rate. Time rate means what? There must be T at the denominator, depending on the time. Time rate flow of electric charges. Q, I is equal to Q by T. So now equation is given by I is equal to Q by T. Already I referred this equation in chapter 1 when I explained about the definition of electric charge. So now if I rearrange this one, I will get Q is equal to IT. Here I use a capital Q is equal to IT. Current is flowing in 1 second is called as what? 1 ampere of current is flowing in 1 second is called as 1 coulomb of charge. There I referred. Same thing here I am using to define the current, that is I is equal to Q by P. What is this? So now this is the electric current I is equal to Q by P. As I said here, if the time rate flow of electric charge through the conductor is steady, this equation holds good. If it is not steady, then for non-steady electric current, then how to measure the electric current at any given instant of time? That means what? Every instant of time. At every instant of time, the time rate flow of electric charge is not uniform. It is varying according to the time. So that means to calculate the current at non-steady time, so then I can use the instantaneous current. That is I is equal to limit delta t tends to 0 delta q by delta t. So this is itself is called as instantaneous current. This is referred as what? Instantaneous current. So we already studied the definition. Now we studied the instantaneous current. After this, let's proceed to the next one. The SI unit. SI unit of electric current is. SI unit of electric current is ampere. Ampere denoted by already we know in the chapter first year capital A. Denoted by capital A. Then the next point is current or electric current in scalar. Current is not a vector quantity, it is a scalar quantity. It is only having the magnitude, no direction. And next thing is the conventional direction of current. Conventional direction is positive charge. That means is flow of positive charge, I can say. So in which direction the positive charges are flowing, that direction itself is taken as the direction of the current. That is conventional direction. That is only the purpose we are indicating the conventional direction. And the next thing is, if we take two conductors are carrying the electric current and they subtend an angle, the angle will not going to affect the electric current. And the electric current obeys scalar addition. It does not obey the vector addition, it obeys laws of scalar addition. Then, friends, few more important topics. So let's take some important things here. Suppose if I take plus q and minus q or two charges are flowing at the time t, in forward direction. I will explain what is meant by forward direction and backward direction afterwards, step by step. So now, if plus q amount is the charge, or let's say plus q charge is flowing at the time rate of t in the forward direction, minus q is also charge flowing at the time t in the forward direction, then the total current of the system is given by I is equal to q1 by t minus q2 by t. This is the current to calculate. Suppose if plus q is in forward direction, and minus q is in reverse direction. Reverse, you can say reverse or backward. Reverse direction in time t. Then I is equal to q1 by t plus q2 by t. One more thing. Afterwards, so one natural phenomenon where we come across the flow of charges from higher potential to the lower potential is the lightning. In the lightning, the charges are released from the cloud to the earth. But please keep it in mind, my friends. These charges are not steady. There is no proper flow of steady flow or constant or uniform flow of the electric charges from the clouds to the ground. So we can say it is a non-steady electric current. Then afterwards, suppose as we know that if lightning carries the electric current, so what is the rate? At what rate it carries the electric? Please keep it in mind. It is very, very, very high. It is a few thousand, 10,000s of ampere of current it carries. At the same time, even in our body, the nerves. So when if anybody taps here this corner, so we'll feel electrical shock. That means what? Even only microamperes of current is flowing in our nerves. So this is all about the introduction of the electric current. Now I hope it is very clear to you people. If it is clear, then let us proceed to the next topic called as electric currents in conductors. Very simple and very small topic. So as we know that we come across three states of material or matter in the nature. One is solid state, another one is liquid state, another one is gaseous state. So now the heading is electric currents in conductors. Electric current in conductors. So as we know that there are three types of matters we come across in our day-to-day life. Let's first take the first one, that is solid state. Second one is liquid state, and the third one is what? Gaseous state. Suppose if you take any metal, as you know that all the metals are good conductors, right? So if you take a metal and if you write the configuration or electronic configuration of that solid, then we come across the valence electrons. Those valence electrons in case of solids are the responsible of the conduction of electricity. So valence electrons are the responsible of conduction of electric current in case of solids. So now if you move to the liquids, so already you are aware of Arrhenius theory of ionization, right? So what this says, so we come across electrolytes. Two types of electrolytes are there, strong electrolytes and weak electrolytes. And when these electrolytes are immersed or dipped or put into water, they dissolve, they split into their constituents ions, right? So if it is strong electrolyte, entire electrolyte or salt will convert into their respective constituents ions. But if it is a weak electrolyte, only few amount of salt is converted into the respective ions carrying positive charge and negative charge, called as cations and anions. Now let's come to the point. So if the ions are present inside the liquid, these ions are itself is responsible of the conduction of the electricity in case of liquid. Called as ions are responsible of the conduction of electricity in case of liquid state conductors. And let's proceed to the gaseous state. If the conductors are gaseous state, then the discharge tubes, they are called as discharge tubes. Discharge tubes are responsible for the conduction of electricity in case of gaseous conductors. So with this brief introduction of the electric current in the conductor, so let us proceed to the one of the very, very important and examination point of view, and this entire physics life is concerned, that is Ohm's law. So now, what exactly Ohm's law says? Plays very, very important role. So let us study step by step Ohm's law. Friends, already you came across two important things at the beginning of this chapter, that is called as potential difference and electric current. First, to allow the flow of charges, flow of the electric charges from one place to another place, what is required? Two potential ends are required. Those two potential should be at the different values. That means there should be a potential barrier, or also called as potential difference, right? Then, if potential difference is there, the electric charges will flow from higher potential to the lower potential. That's good thing. Already we have this one. Then we have one more thing. Suppose let me take one simple concept. So here representing Ohm's law. Ohm's law. Suppose if I take a conductor, so in this conductor if I take A and B, so A and B, if the electric charges are flowing from B to A, then means this higher potential is at a lower potential. So let me take this is V2, this is V1. So if I write the potential difference between them, so let me write V is equal to V2 minus V1 or V2 difference V1 like this. So potential difference is there. If the current is flowing from one end to the another end, so current is flowing, so symbol of current is say already said I, it is I. So it's flowing. Now the question comes, what is the fundamental or the basic relation between I and V? So now there is a potential difference V is there. When the potential difference is there, the electric charges are flowing from one end of the conductor to the another end of the conductor. Question comes, will they flow very easily? Or will they experience any opposition? Or without any hurdle they will move? That question comes into picture. So George Simon Ohm, right, scientist, a physicist who thought of this, right, then he gave very fundamental and basic knowledge or to relate the potential difference and the current, right. What he related, so if electric current is flowing through the conductor, if the electric current flowing through the conductor and this electric conductor is directly proportional to the potential difference across the ends of the conductor, what is here in this statement? So let me write the statement. He said that the electric current through the conductor, is directly proportional to, he said this electric current is directly proportional to the potential difference across the ends of the conductor, There is a condition that the electric current through the conductor is directly proportional to the potential difference across the ends of the conductor. Condition applied provided temperature and other physical quantities. He says there shouldn't be a change in the temperature. If there is a change in temperature, V is not perpendicular to I. First thing. Second thing he says, if there is a change in the pressure, he said some physical quantities, pressure, temperature. If these are the physical conditions, if they remain same, then he says that the electric current, I is directly proportional to V. Both are uppercase, I is directly proportional to V. Then, if I replace this by a proportionality constant, I can write here I is equal to V. So then, once if I remove this proportionality by equal to sign, I must use a constant. The constant is given by R. So I is equal to V by R. So if I rewrite this equation, I'll get V is equal to IR. One more very important 3-variable equation. V equal to IR. Then what is R here? Where R is called as proportionality constant. Where R is proportionality constant. is called as resistance. Then if I rewrite this equation, I will get R is equal to V by I. Then how to define the resistance? The resistance of a conductor is defined as ratio of the potential difference across the ends of the conductor to that of the current through it. So if I write the definition of this, then resistance. Let me write the definition of resistance. It is the ratio of potential difference. Is the ratio of potential difference across the ends of the conductor. Across the ends of the conductor. Ends of the conductor to that of electric current. To that of electric current through it. Through it means the same conductor. When same current is flowing through the conductor and the potential difference across the conductor, then if I take the ratio between them, that is V by R, then we will give the resistance. Resistance is nothing but V by I. Friends, here I am using the word resistance. Don't confuse with the thing. The dictionary meaning of resistance is nothing but opposition. It is also defined as, the resistance also is defined as, one more definition is opposition offered by the conductor to the flow of electric charges through it. That means when the charges are flowing inside the conductor from one end of the conductor to the other end of the conductor, here I show you the red color I. Then resistance R, I will show you the green color. Resistance R come into picture. R will not allow all the electric charges flow through it. It opposes. The opposition offered by the conductor to the flow of electric charges through the conductor is called as what? Resistance. I hope it's clear to you people. Then the SI unit of resistance. Resistance is measured. R is measured, or the SI unit of measured, or SI unit of resistance is measured in special word ohm. It's called as small o, Hm, symbol is omega, ohm. Then if you take borrow same equation, here on the right, R is equal to V by I. If V is equal to 1 volt, I is equal to 1 ampere, then R is equal to 1 ohm. Then how to define 1 ohm? So here on the V equal to 1 volt, I equal to 1 ampere, then R equal to 1 ohm. The resistance of the conductor is said to be 1 ohm if 1 volt, the 1 volt of at the potential difference 1 volt, let's say 1 ampere of current is flowing through the conductor at the potential difference of 1 volt. You can say in any way, or else you can say let's say in the ratio only. It is the resistance of the conductor is said to be 1 ohm when the ratio of the potential difference is across the ends of the conductor is 1 volt. Then the current through the conductor is 1 ampere. You can define it many ways. So I repeat. So when 1 ampere of current is flowing through the conductor at the potential difference of 1 volt, then the resistance of the conductor is said to be 1 ohm, or resistance of the conductor is said to be 1 ohm when the ratio of the potential difference across the ends of the conductor is 1 volt, through which the current is flowing at the rate of 1 ampere. You can define it in several ways. Now, after this, R is depending on. So I will not write the definition of ohm. You can just by seeing the notes you can write afterwards. So then R is depends on, or R is depending on. This is very, very important. R is depending on. First one is material. It is depending on material. The second one is geometry. Geometry means shape of the conductor, and geometry means shape of the conductor. And what is the shape of the conductor? Based on that, the R is depending. Material means, and what material? It's copper, aluminium, gold, aurum, or else argentinum. It's called as silver. Based on which material is made up? Material, geometry, and the third one is temperature. So So now it's depending on the temperature. We are going to talk about this one, temperature dependence of the resistance later, the next topic. Don't need to worry about this. So R is depending on the material, geometry and the temperature. Now friends, if several experiments were conducted, then it is found that the dependency of the resistance, dependency of the resistance, it is found that it is experimentally found that R is number one directly proportional to length of the conductor L, length of the conductor, and inversely proportional to area of the conductor. What is the meaning of this? That means very simple. As the length of the wire or the conductor increases, resistance increases. As the area of the wire increases, thickness increases, resistance decreases. So if I write mathematically, I can write here R is directly proportional to L and inversely proportional to area. R is equal to L by A. After this, if I remove this proportionality by a constant, then I can write here R is equal to L by A as it is. But in the place of proportional, I have to use a constant, and that constant is given by rho. What this rho is called as? Rho is called as, two names are there for this rho. It is called as resistivity. It is called as resistivity. One more word is called as specific resistance. Specific resistance. It is also called as what? Specific resistance, and also called as a resistivity. Right. Now, after this, from Ohm's law, we know that. From Ohm's law, what I know that V is equal to IR. Wherever R is there, I have to substitute this equation. If I substitute, what I will get? V is equal to I into, in the place of R, I am using this one, rho into L into A. Then if I rewrite this, I get rho into L into I by A. There is a reason why I am writing this only in the bracket I by A. There is a ratio here, current per unit area. This current per unit area is there, no? This current per unit area is called as current density. Current per unit area is called current density. Very, very important. Current density. Current density denoted by small j. Then J is equal to I by A, and it is measured in terms of ampere per meter square. Look at this, current is measured in terms of ampere, area is measured in terms of meter square, then J is equal to I by A, and very, very important thing is, it is a vector quantity. Please keep it in mind, very, very important. It is a vector quantity. That means what? Current density is a vector quantity. So now we arrived at this equation, that is, I can rewrite this equation, that is Ohm's law. V equal to rho L is there. No? This equation I can write in another manner. What is that? Let us see. So let us write this equation. So we get V is equal to J into rho into L. This is equation number 1. Very, very important. Then, if it is a steady current, then let me consider some important things here. If E is the electric field inside the conductor, as I said at the beginning, so if E is the electric field inside the conductor of length L, then there is a potential difference across the ends of the conductor. Just recall the relation between electric field and electric potential. Let me write that one. If E is the electric field, right, electric field of conductor or inside the conductor, in the conductor of length you know that? We know this one. E is equal to dV by dr. Second chapter. So now, if I rewrite this one, here I have taken V divided by L. So I can write here V is equal to E into L. This equation already I wrote in the second chapter too, because some important equations will be useful in the previous or the next chapters, previous topic or the earlier or next topic. So that is why at the beginning only I have a foundation. So now equation number 2 is here. So this is also potential difference V equal to J into rho into L, and it is considered the current density, resistivity and the length of the conductor. This is the potential difference with respect to the electric field. From 1 and 2 I can write here. From 1 and 2 I can write EL is equal to J into rho into L. L will get cancelled. So E is equal to rho into J. Bring this rho this side. So this becomes E by rho is equal to J. So J is equal to sigma into E. So in vector form, if I write this in vector form, so one step here only. So cancel L and L, bring this rho this side. So this becomes E by rho is equal to J. So if I rewrite this one, J is equal to sigma into E. So that means what? See vector in vector form, sigma is equal to J equal to sigma into vector E. This is vector form of Ohm's law. Ohm's law. Here I have one important difference. Look at this. So I said here rho is nothing but what? Resistivity. This is what is called as resistivity. So now 1 by rho is equal to, I wrote sigma. Sigma is nothing but what? Conductivity. So what is the difference, main difference between these two words, resistivity and conductivity? Reciprocal of conductivity is called resistivity, or the reciprocal of conductivity is called as resistivity, or the reciprocal of conductivity resistivity is called as conductivity. Both are mutual. That means it opposes, it permits. It permits, it opposes. Both are mutually perpendicular to each other. So I can say the resistivity is depending on the conductivity. It's inversely proportional to the conductivity. So as conductivity increases, resistivity decreases, or vice versa. And you are going to calculate the resistivity of a given material in the laboratory. That is one more thing, that will be practical aspects. So now with this, friends, I am closing this topic. So that is introduction of the electric currents of the conductors and Ohm's law. In the next class, we will study one more important topic. Thank you.